Welcome to the third part of our little installment here on suitability modeling. And I'm Dr. Michael Harmon. I'm the uh, GIS program head at Northern Virginia Community College, and I'm making this video primarily for one of my classes so that they have an opportunity to uh, see all the little pieces that we learn from week to week put together in the context of a larger problem. And I'm also putting these things together because um, as so many of us are now landlocked in our own homes, uh, settling in and staying in place and avoiding unnecessary travel and such things, an opportunity uh, exists for all of us to grow and to learn. And some people have an interest in GIS, and if one person has a better understanding of what we do and what we can do because they've watched this video or this series of videos, then it's been well worth the time and effort to do so. So we're in the third step in this process, and this is the one where we standardize way and do some map algebra. This is sort of the meat and potatoes, if you will, of the model or the modeling process, or if you're a vegetarian, perhaps we'll call it the beans, nuts, and potatoes of the project. So let's take a look here and see exactly what we're going to do next. One of the most important steps is standardizing your data. Why? Because it's hard to add meters of elevation to a tree type. What does 900 meters an elm equal? It equals nothing because the units are so different, and even if they were all numeric, if they were one in the thousands and the others in the tens or the hundreds, you can see how subtle changes in one data set could overwhelm the other. So we have to standardize these variables before we combine our data if we want to get meaningful output. And so how do we do that? Well, we apply just basic and in some cases advanced GIS concepts to convert or classify everything into the same scale. Now, we have two basic data sets in our model, our digital elevation model and our land cover. And so we're going to look at how we can standardize both of those. And we're going to look at how we can do both of those relative to a more detailed example that I'm going to show, and sort of the kind of generic scaled down bare minimum kind of version that I would expect a student to try the first time that they're doing a project. And so basically you have this sort of Borling kind of model where looking at elevation, if in our case the habitat number is 900, that squirrels, relatively speaking, flying squirrels, only like it above that elevation, then everything below that number gets a value of 0, and everything above will get a value of 100. Pretty straightforward. Yes, no, 1, 0. In our case, it's 1 or 100. Now, for my model, I'm looking at a slightly different piece of documentation, and the paper that I was looking at said that they rarely found these squirrels below 700 feet in elevation. 700 meters, I'm sorry. So that gave me a lower starting point. But they found the most evidence of these squirrels at around 1,036 meters. Okay, so what I decided to do was to create a fuzzy membership function, okay, where my relative value goes from 0 to 0, from 0 up to 700 feet, 700 meters. And then as we go from 700 meters to 1,036 meters, that will gradually increase from a score of 0 to a maximum value of 100. And then as we pass 1036, and we go on up to 1482, which is the highest elevation in the state, that relative standardized score will then start to decrease. And so I have a decreasing function then that goes from 1036 up to 1482, values going from 100 down to 0. Now, as far as land cover goes, same kind of scenario. Students will pick the ones that they like best and combine those, relatively speaking, all as being equal. Maybe they pick 3, maybe they pick 4, maybe they pick 7. They can justify that however they want based on the information. But for me, I'm going to look for like the 4 best force types that I think I can identify in this data set. And the best one's going to get a score of 100. And the next one's at 80. And the one below that's at 40. And the one below that's 20. And everything else I'm going to give a value of 0. Because I'm not going to create this simple 1, 0, yes, no, true, false kind of model. I'm going to create more of a true index model to where I get a numeric value that I can literally look from place to place and see how suitable the habitat is. So this is our model we started with last time in GIS. This is just the basic kind of map document that I was working on before. It has the land cover data set and the elevation data set. You remember the the land cover data set, we wanted it to be in a different projection, so we had to reproject it. And one of them had some projection information missing, so we had to go in and add that information in. And so we got all that fixed in video number 2. So now we can actually start to do some of what we're doing. So if I pop open the attribute table and start looking at it, I really don't have much there, but you see I've got the row ID, I've got the value, and I've got the count. The value is that elevation figure, and the count is the number of cells that have that value. I'm going to go up there in the upper left where that little red circle just appeared, and I'm going to click on that, and I'm going to go to add a field. And I'm going to call it new ele, which is my shortcut for a new elevation. It's going to be short integer because it's nothing super big there. Leave the precision and stuff alone, and I'm going to click OK and go on. So once I do that, I get that new field. The next step for me is I'm going to use the select by attributes function, which is right up there on that header across the attribute table, and I'm going to create a new selection where value is less than 700. And you can see there how I've got that set up. So again, there's the tool inside the red circle. That's the select by attributes GUI that opens up. The next thing I'm going to do is standardize my DEM. I'm going to do sort of both examples, the student kind of example at the top and then my 0 to 1 scaling example. And I've got 2 different functions I'm going to use. Well, realistically, I'm going to use 3 selections and 3 calculations. The first selection, I just equal things to 0. The second selection, I'm going to use that increasing function where my values go from 0 at around 700 up to 1036. To where the value will then be 100, and then from 1036 down to 1482, it's going to go the other direction. I apologize, I can't make a video without yawning. That's why I'm not ever going to make it in the movies. Anyway, so that's the basic setup of what I'm going to do. You can look at these equations if you want. I'll kind of go over the first one just a little bit. The value is the numeric value field that you're operating off of, and in this case it's going to be elevation. So it's that value minus the minimum value, and that calculation is going to be divided by the maximum value minus the minimum value. And then once I add those 2 together, it's going to give me a percentage. But decimals and rasters can be a grind sometimes, and so to avoid all that, I'm going to multiply all that by 100. And so basically, I'm going to end up with everything going, all my outputs are going to be between 0 and 100. Okay, let's see what happens next. Okay, so let's take a quick look at how this all works. Basically, once I've added that new field in, I'm going to then select that field just by clicking up there where it says New LE. And once I've selected it, I'm going to use the field calculator, which pops up and it just asks me what new LE is going to be equal to. And I just put in 0 because that's what I want. And you can see over here on the left with my select by attributes feature, the only thing I did was I've just looked for, well, my next step after I've made all of them zeros is to then make my second selection. So initial selection, everything's 0. Next selection, everything above 700. There's 700. There's the field. Here's the calculator. This is the equation that I put in. And this is going to get me that second step. This is going to get me from 700 up. And when I'm selecting my maximum values, I know that my next breakpoint's at 1036, so I don't need anything any higher than that. That's the only thing I'm going to use. If I use a higher number, it's going to mess it all up. So once I've run that, you can see the attribute table, then it gets updated. Everything that was below 700 still has a value of 0, and everything above 700 slowly starts to increase in value, and as you were to scroll down the list, it would eventually reach 100 at or roundabouts 1036. So the next sort of phase in the step is to repeat the process. But now I'm going to clear my selected features, and then I'm going to again click on the new LE field. I'm going to do a select by attributes. I only want everything above 1036. Once that's selected, they'll be highlighted. You can see here 1037 above, it starts to turn blue, so they're highlighted now. I can now go up, right click on the new LE label at the top of the column, and start putting in my field calculation. And same calculation as before, value minus minimum over maximum minus minimum times 100. But now I need to flip the direction, so I got to put a 1 minus in front of that equation, but before the 100 at the end. And it'll look kind of like this. I've updated my minimum and maximum values. My minimum value now is 1037, and my maximum value is now 1482, because now I'm doing that last chunk of the elevation data that goes from 1036 up. Okay. So now the elevations are reclassified, and we've got this new raster. But as you remember, rasters only have one value, and we just added a whole nother field. In order, if we're going to make that field really useful, we need to just go ahead and convert it into its own raster that has that value. So our next step, we're going to go look at and use the lookup tool. And lookup is in Spatial Analyst. It's inside the reclass toolbox. And the lookup toolbox, it's only got a couple of inputs there. We input the raster, which is our West Virginia NED, and then we're going to add in our lookup field, which is what we're going to make the new raster from, and that of course is our new elevation field. So I did that, and then I have to select the output. Now what it's going to do is automatically send it to a default. But I'm going to click on that little folder there and tell it, no, I don't want it to go a default. I want it to go into my Data 2 folder where it's supposed to go. I'm going to give it a new name called Reclass LE. So again, lookup tool, put in my inputs, give it a new name, and save it somewhere where I know it's supposed to go. And once I do that, I get an output that looks like this. This does not look like the elevation data we had before. But it doesn't really make a lot of sense either. So I'm going to do a little work to clean it up to make it look a little more presentable. And to do that, I'm going to go to the layers property for this particular piece of data. I'm going to go into the symbology, and I'm going to go from the sort of classified way it was into a stretched format. I'm going to stick with the same color ramp and just apply that and see what it looks like. And now you can see I've got this a little better look, and now it goes from the yellow, which being 0, to the dark blue, which is values of 100, and the greens are in between. So that kind of makes sense. So the next step in this process would be to look at how we could do this from a student standpoint. So if we're a student, we're going to reclassify just like we did before, but we're going to change it a little bit because we don't need, all these different values, and we're not going to go in and reclassify it by doing a calculation. We're just going to do a simple reclassification by using the reclassify tool. It pops up. We're going to classify. We'll have some options there with the classification. I'm going to set it to 2 classes, and then I'm going to make that first manual breakpoint where the student would want it, in this case 900 meters. So, reclassify tool. Once that tool opens up, we're going to use the little reclassify tab. We're going to set our classes to 2, and we can just manually type in that number there at 900 we want. You could also grab those lines coming up from that histogram and drag them around to wherever you want, but it's easier just to type them in there. And then click OK, and OK, and OK, and run everything. Always remember, look at that output. Where is it going to go? Put it in the folder where you want it. Give it a name so you'll know what it is. The next step after that is to do a little more work. So once we click that classify button, it's going to then give us that new classification we have of just everything to 900 and then 900 and above. And we have an opportunity now to put in a different value. And so what this would have defaulted to is a value of 1 and a value of 2. But I'm going to change that. Why? Because I want everything below 900 to be a value of 0 and everything above 900 to be a value of 1. But if you're looking here, you see I didn't use 0, I used no data. No data is a clever way of getting rid of unwanted processing. So by making that no data, what I've done is I've just scrubbed away everything so that the only thing that's left is the values of 1. If I do this with my other data set as well, when I combine them, the only outputs I'll get is stuff that intersects the 2 data sets basically. And so that's just another way of doing that. Again, always remember, what are you calling it? Where are you saving it? So make your changes and then look at your location. Make sure it's in the folder you want. In my case, it's data 2 on my desktop. And I'm going to call this student elevations and then click OK. And once I do that, voila. That is everything that's above 900 meters in the state. Next up, let's talk about standardizing the forest types. This is actually not as easy as what you might think. To begin with, you're just going to get these names: mountain conifer, mountain hardwood, industrial, and what have you. You have to go through and figure out which of these land use or land cover classifications warrant your consideration. Okay, so if you actually go into the folder where you unzipped the GAP land cover data set, you'll see there's a text document in there called Notes. And there's also a Word document. But if you open up one of these two, what you're going to find out is you got detailed explanations of the composition of the various classes of land cover. And so you can then decide which ones you think are appropriate for what you're doing. If you display all of them by the names, you see there's a lot of different categories. What I'm going to do is reclassify those categories based on my own criteria. So I'm going to use the reclassify tool, which is in reclass, which is in Spatial Analyst. The reclassify tool comes up. I'm going to select the output location that I want, give it the name I want. I'm going to call it New Forest. And I'm going to classify it, but I'm going to reclassify it by the name field. And that's not going to be the one that pops up automatically, so you're going to have to change that a little bit. But once you do, it gives you an opportunity to go in and make some changes. So, recap. I'm going to use the reclassify tool. I'm going to change the reclass field to name. That way the old values of like bare land and conifer plantation and cove hardwood come up. Then I'm going to, for each of those land cover types, assign the value that I decided on. And remember, I picked 80, or I picked 100. I picked 20, 40, 80, and 100. And so, based on the rank and how many points it was, the one you can see here in this example is the cove hardwood. I gave it a value of 20, and so that's there. And you see all the rest of them are zeros. Full disclosure, I made a little boo-boo when I did this. Somewhere along the line, I didn't get one of the values right, and so I ended up with a kind of a goofy output where I had a -1, which is kind of a default for something's not quite right sometimes. And so I had to do an extra reclass step in there to kind of fix it. The alternative was to go back and do it all over, but it was just easier for me to fix it. So I didn't actually show you the steps on that, but I didn't want you to, do everything exactly necessarily the way that I'm doing it. And then when the output comes out not quite the same, you'd wonder why. All right, so moving on from that, I gave it a name, and here we go. That's my output. You can see over there in the table of contents, I've got no data, shrub, land, woodland, so it combines all those categories. And then I've got cove, mountain, mountain, and mountain. That's the 4 that I selected. But remember how rasters can only have one field, and we just added another field? Well, I'm going to use that same tool we used earlier, which is the lookup tool, which is in the reclass. And I'm going to put in my input raster as new forest. And my lookup field will now be value, which is where I gave it the 20 or the 40 or the 60 or the 80 or whatever it is. And then I'm going to assign a location for it where I want it, which is in my data 2, and I'm going to call it new forest 2. Once I've done that, you can see what new forest 2 looks like, and you can also see that the majority of this data is my 0 category, and then I have some in the 20, and I have some in the 40, and some in the 80, and some in the 100. If I was doing the student style, this would be a lot easier. If these are the ones that I selected, mountain conifer, mountain hardwood, cove, those would all get values of 1s. So the rank is more or less irrelevant. And everything else would end up in the 5 or the, nah, that's a 0 kind of a value. So let's take a look at what that would look like. I'll go back to the original GAP land cover data set. I'm going to use the reclassify tool, same as I did before. But now when I go down through that list, I'm going to, again, switch it over, my reclass field to name. And then from name, I'm going to convert all the classes of stuff that I don't want into zeros and all the ones that I do into 1s. Select the location where I want. Output raster, give it a new name. I'm calling it LC Stu, which is land cover student. It's my sort of abbreviation. I'll save it and run it. I also want to make a couple changes to the symbology when this layer is going to run. So I'll show you what I did, and then you can see how different this looks. So I'm looking at the unique values. I only got 2, 1s and 0s, and so I can set that up to make it look the way I want. And then my new land cover stew data set now looks like this. 1s is habitat potential, 0s is not suited for habitat. So before we get much further along, let's go ahead and finish out that basic student type model, because I know that's what a lot of the people that are watching this wants to do. So we'll just kind of jump ahead there a bit. Next step is map algebra, and it's really not complicated. You're simply going to multiply your data sets. If a location has a value of 0 in either data set, it ends up as a 0. Elevation and land cover in a typical student model are not weighed any differently. They're weighed equally, so there's no weighing step to consider. The land cover layer is also a Boolean layer where it's 1s and 0s or 1s and nothings. Same with our elevation. Ultimately, if we multiply these out, anything with a value of 1 is habitat. Anything without a value of 1 is not habitat. So let's take a look at what this looks like. Okay, in Spatial Analyst, under Map Algebra, we fire up the good old raster calculator, and selecting from the layers under my Map Algebra Expression tab, I select LC2, which is a student land cover layer. I'm going to multiply it by student elevation layer. I'm going to pick the output place that I want. In this case, it's going to be Data 2 folder, and I'm going to call this Habitat Model 1 or HabMod 1. And it ran. Now, I've got zeros and ones. I'm not really interested in the zeros. I'm more interested in the ones because the ones are the habitat. And so I'm going to go ahead and do a quick additional reclassification step, reclassify, just to kind of get rid of it. And I'll show you sort of the benefit of why in a second, or tell you about it. I did the reclassify off the value field. The old values were zeros and ones. In the new ones, I converted all the zeros to no data. And the reason is, this is going to clean up this data set so that I just have the habitat. Because sometimes you might do something like this because you might ultimately want to convert that raster into vector data. And if you can go ahead and eliminate everything except for the stuff you want, it makes that a little easier. And so it's just a good habit to get into. If you no longer need the zeros, clean them up. And so I did. I just reclassified them as to nothing and made them go away. And when I did, that's what I have. That is the habitat for the student model. If you open up the attribute table to it, you can see that there is, let's see here, 4,028,516 cells. Each cell is 30 meters wide by 30 meters long. Turns out, if you take that 4,028,516, that's the count, and you multiply it by the width, that's 30. You multiply that by the height, which is also 30, and you divide it by 4046. 4046, that's the number of square meters in an acre. It'll convert that count number into the number of acres, which in this case is just under 900,000 acres of potential habitat in West Virginia based on the student model. So let's get back to my model now, and let's look at some of these other interesting things we can do. And let's talk about how we can add weights to what we're doing. So here's my logic on this. Flying squirrels do not have altimeters, so they don't know if they're in the right elevation range for their habitat or not. But what I like to say is squirrel got to eat, right? I mean, squirrel got to eat. If you're living up on top of the hill above 700 feet, 700 meters, and you're hungry and there's nothing to eat, and on down the hillside there's stuff that you could eat, are you just going to sit up there and die of starvation? Or are you going to go on down the hill outside of your elevation range and have yourself a snack? So I'm going to give my informed decision to weigh land cover as more important than elevation because squirrels don't have altimeters, and like I said, squirrel got to eat. So the way I'm going to divide this up is a technique that I think is really simple and it's easy to use, and I like it pretty good. I just work off of 100%. And so I'm going to divide 100% up between each of my categories, or each of my inputs, and so that my sum total has to equal 100. And so I'm going to assign more importance to land cover than I am to elevation. But here's the thing. Elevation controls so much in these environmental index, in environmental and process type models. It's just ridiculous. So much of your ecosystem is controlled by elevation. Everything from how much rain you get to how quickly you dry out. A lot of that is controlled by elevation. And elevation then controls which species of trees will grow. And so there's a lot of collinearity between these various parameters. And so I'm not going to weigh this wildly one way or the other. I'm going to, because they are interrelated, but I do feel like the land cover is a little more important. I'm going to weigh it 55-45. If you add those up together, you get a total of 100. I'm going to give 55% to land cover, 45% to elevation. So let's run through my map algebra example. Multiply my data sets, locations with zeros, always end up with zeros. If a location is perfect, what does that mean? Well, if we have an elevation score of 100 and I multiply that by 45%, I'm going to get a value of 45. If my land cover is perfect and I multiply that by 55%, I'm going to get a value of 55. So if I multiply 45 times 55, the maximum value I can get in my index model is 2475. So the closer I am to 2475, the better the location. The lower, the worse. And I can display this a lot of different ways, and we'll look at some of that. Mostly we'll look at that in the next video, but we'll touch on it here. So how does this look? Well, I go back again, spatial analyst, map algebra, raster calculator, and I bring in raster calculator, and I take my new forest 2A, which is the corrected layer that I had to do because like I made a little boo-boo earlier I mentioned. So I fixed it, and that's what I called the fixed one. And I'm going to multiply that by the weight that I assigned to land cover, which was 0.55. And I'm going to multiply that in its total by my reclassed elevation layer, which I'm going to multiply by 0.45 because that's the weight that I assigned to that. So both of these variables have been standardized to numeric values between 0 and 100. And then I have weighed them accordingly in multiplying one times the other. And I've selected my output location. In this case, it's again my data 2 folder, and I'm calling it Dr. H mod, which is Dr. Harmon's model. And there we go. Now, looking at this at first, I really don't like the direction of the scale to where the low values are dark and the brighter values are the higher values. And so I'm going to do a little bit of a reclassification so we can see it a little bit cleaner. And what I did was I used the Jenks classification method in the layer properties under symbology. And I wanted a number of classes, 5 to be exact. And then I excluded all the 0 values because I don't want them to be part of one of these classes. And once I did that, it picked the natural breaks based on creating classes that are more like themselves and as different as possible between one another. And so then, instead of leaving the numbers, I just went ahead and converted it into sort of a text moniker, if you will. And I took the lower values, and that was going to be the poor quality habitat, and I called it poor quality habitat. And as that value increased, I called the next class moderate, and the next one was good, and then the darkest to last would be the highest values, the closest to that magic number I was shooting for, ended up being the best quality habitat. And when I map those out, you can see how that then looks at this. Now I can also open up the attribute table, and I could look at this in a lot of different ways. I could figure up any number of these and just select the values from A to B, 1 to 2, whatever it is, and calculate up the individual amounts of each of these habitats. But for the purposes I'm looking at here, I'm just going to throw that on there so you can kind of see where we're talking about. And if you go back to what I said in video 2 about not worrying about the projection, that line that divides zone 17 north and the next zone to the right is over there in the eastern panhandle, sort of between Martinsburg and Frederick. It's just the very tip end of Jefferson County in West Virginia, and as you can see, there is no habitat there, and so it's not going to impact this at all in any possible way. But as you look across the rest of West Virginia, you do see there's scattered pockets here and there and faint traces around, but the majority of the good and best habitat follows right along that Appalachian plateau along the Allegheny front as it moves down through the Appalachians there. That's where these flying squirrels live. That's where my habitat model shows. And so next video in the series, we'll look at different ways we can make some maps and tables to sort of showcase some of this information and how we can add other data in here depending on what questions we might have. And so if you like this video, look forward to the next one. Let me know. Leave a comment, a like, or what have you. It will be appreciated. Thank you.